Hey everyone, welcome to a topic revision video for A-level physics. This is a new series that we're going to be starting, and we're starting with the first chapter in the A2 syllabus, which is the motion in a circle. Now, in IGCSE maths, we learned about the circle properties and circle theorems, so we are already familiar with some terminology. So we know what radius is and we know what arc represents. We know what the angle subtended at the center is. We know what the diameter and the radius are. And we know what the full circle length is called, aka this is circumference. So the new terminology or the new terms that we uh, have to learn, just to list them first and then we will uh, define the important ones. This theta, first of all, is our angular displacement. We will define it in a second. We know r is the radius of the circle. These are the symbols that we are going to be using forward into the syllabus. S will be representing the arc length. V will represent the linear speed or velocity. In some books, this is also written as tangential velocity or tangential speed. We will explain that in a moment. Then we have omega. This is not W. This is the omega, the Greek word, a Greek letter, is the angular velocity. Since we're talking about circular motion, so obviously we have to talk about the circular part also. Centripetal A would be centripetal acceleration, and last but not the least, centripetal force. These are the terms that we need to be good with. At least we should know what the symbols mean and what they represent. So theta is the angular displacement, r is the radius. You could have d for diameter also. S is the arc length. V linear speed velocity, that represents orbital speed, the speed at which the object is traveling on this circle. This would be the linear speed. However, the tangential speed, same thing but represented as a vector. So this would be tangential velocity. So speed is the same, but since we're talking about it in terms of velocity, this would be this. And if you haven't noticed by now, this is tangent to this circle. And we know the circle properties that it will be 90 degrees to the radius. We will explain what the tangential velocity is in a second. Omega, angular velocity, is the rate of change of angular displacement. And centripetal acceleration and centripetal force, they are simply related by Newton's second law. Now, so angular displacement, there are multiple different definitions for this. Easiest one to remember is that this is the angle subtended at the center by an arc that's it, angle subtended at the center by an arc. You could also say that this is the angle swept out or angle through which an object moves during a circular motion. Now, the units for angular displacement is the radian, rad. We often represent the angle, and the C on the top represents that this is the angle in radians. And obviously, this is a scalar quantity, not a vector quantity. Next up is the arc length. We already know what arc length is. This is the distance covered or the distance moved by. So the arc length is actually the distance moved by an object moving in circular motion, moving in a circular path or a circular arc. This is represented by S. However, in IGCSE, we know that if angles are represented by radians, S would be equal to r theta, where r is the radius, angle is in radians, S is the arc length. Okay, so you could also remember the IGCSE rules for this. So for example, if you have angles in degrees, you have degrees divided by 360 times by the 2 pi r. However, we know that the pi radians represents 180 degrees or 2 pi radians represents 360 degrees. So if you change the angle to the angle in radians, 360 to 2 pi, and this remains 2 pi r, so the 2 pi and 2 pi gets cancelled, so we are left with r theta, and this theta is in radians. So this is an important point. Theta is not in degrees. So where theta is in radians. Okay, now comes the definition of radians, and that is a very important and very frequently examined question in the syllabus. So it is the angle subtended at the center of a circle by an arc of length equal to radius of the circle. So what that means is if you have S is equal to r theta, so theta would be a ratio of S and r. So if S is equal to r, this transforms into theta is equal to 1. So this would be the 1 radian. So if S is equal to r. So the definition of radian, it is the angle subtended at the center of a circle by an arc. This is an important keyword over here, subtended at the center by an arc of length equal to the radius of the circle. Next up, we have the angular velocity and the linear velocity. Velocity, which is represented by omega. Now, the angular velocity is just the rate of change in, or rate of change of angular displacement. So our omega is basically the delta theta over delta time. This is in stark contrast with velocity is equal to change in displacement over change in time. So this is the circular analog of the same thing. Now, if the change in angular displacement is 2 pi radians, that means basically a full circle, and this happens in time t, which is the time period, which we are going to represent it as a time period. So time period is basically the time in which we full rotation or full oscillation is done. So the omega becomes 2 pi over t. Okay, so where t is the time period. You can also define the time period now. So time period t is the time it takes the object to move around the circular path. Or time it takes for object object to complete one rotation of circle. In my opinion, the second one is better. Now, since this is time, the unit for time period would be seconds or s. Now that we have defined time, we can go into defining the units for angular velocity. Omega, because we use more than one. So the SI unit for this is radians per second, or radians s minus 1. Radians per second, actually they mean the same thing. Why? Because omega definition was change in angular displacement over change in time. This is in radians, this is in seconds. However, we also sometimes use the non-SI units also. Some of them are RPM, revolutions per minute, and RPS, revolutions per second. And we need to be able to convert from RPM and RPS into the radians per second. How we can go about doing that? So, for example, one revolution per minute, one revolution, we know in radians is 2 pi radians. Divided by 1 minute, convert it into seconds, this would be 60 seconds. So this would be pi over 30 radians per second. So basically 1 revolutions per minute or 1 RPM is actually pi over 30 radians per second. Similarly, revolutions per second, again, use the same thing. So 1 revolution is 2 pi radians divided by 1 second divided by 1 second. So that would mean that 1 revolution per second is 2 pi radians per second. So basically that's it. Now, this was the angular velocity. What is the linear speed and tangential velocity? So linear speed, which is also referred to as the orbital speed, is the rate of change of distance covered. Rate of change of distance covered by an object moving in a circular path. Since the rate of change of distance, we know that this is going to be change in distance over change in time. However, we know that for one full circle, for one full circular rotation or one full revolution, the distance that it covers is 2 pi r. Okay, so 2 pi r. So the earlier equation, this equation, transforms into v equals to 2 pi r, and in one full rotation, we wrote above also the time it takes for one full rotation, we refer to it as period or time period. So delta small t is capital T, so this will become t. Now, notice one thing. Omega itself was 2 pi over t. So if you notice this part over here, this is the omega. So V is equal to R omega. So this is how the linear speed, orbital speed is related to the angular velocity. Now, speaking of velocity, the linear velocity or the tangential velocity that is slightly different from linear speed. How? So if we draw the circle, this is the center, this will be the orbital speed. Oh, sorry. Orbital speed just to differentiate between linear speed and linear velocity, this is the orbital speed, rate of change of distance covered. However, the velocity part involves the direction. So it will have the same magnitude as the speed, but it will have a directional component also. So if if the object is moving clockwise, the vector tangential velocity or linear velocity, it will be moving this way throughout the rotation. It will have the same magnitude because obviously the speed is the same. Now, what does this direction represent? It represents that if, for example, the connection between the object and the center is eliminated, the object will move off in this direction. This is why it's called tangential velocity. Now, the next important thing, since we have talked about the tangential speed also, the next logical thing is the acceleration. A, or the more appropriate word, centripetal acceleration. Also N. Now, the basic definition for that is that it is the rate of change of velocity. However, we are going to delay writing the definition because there's an important aspect to it. Now, if you notice this change in velocity over here, so let's call this u and let's call this v, initial velocity, final velocity. We know that a is basically the change in velocity over change in time. So if we look at this in a vector point of view, so vector point of view, v minus u over t. So v is, let's say, this. U, when you do the minus thing, it will be going upwards. So the direction part, v minus u, is actually going inwards. Okay? So that means that if we bring u to be very close to it, very close to it, very close to u, for example, and we perform the same thing, v minus u. So v and the minus u would be looking like this, somewhat like this. This is the minus u. So the v minus u would actually look like this. This is the v minus. So this is not a coincidence. It's actually directed towards the center of the circle. Okay, so this is the directed towards the center of the circle. So this is the direction of acceleration because this is the direction of change in velocity vector also. So this is the definition of acceleration, is that it is perpendicular to velocity. So this is the definition of centripetal acceleration, and this is the definition of circular motion also, that acceleration is perpendicular to velocity of an object. So the definition is that the centripetal acceleration is the acceleration that is perpendicular to the velocity of an object moving in a circular path. Now, this definition is very important because this is the definition of circular motion also, that the acceleration is perpendicular to the velocity of the object. When acceleration is perpendicular to the velocity, automatically the motion will be a centripetal motion, circular motion, sorry. Either way, that's the same thing. Now, the derivation of acceleration equation is not part of the syllabus, so it's just v squared over r. And if you use v is equal to r omega, this could also be written as r omega. This is all that's in our syllabus. Now, whenever there is acceleration, there is force also, due, uh, which is explained by Newton's second law. So we know that according to Newton's second law, wherever there is an acceleration, there is a resultant force also. So in this case, force is the centripetal force and acceleration v squared over r or mr omega squared. Either way, this is going to be represented like this, where r is the radius of the circular path. How do we define this force? It's also important. So centripetal force, we will define it similar to acceleration that we find, but slightly different. A force perpendicular to velocity of an object and directed towards center of the circular path or center of the circle required to keep the object in circular motion. That is important. So force is just like acceleration, is perpendicular to velocity of an object directed towards the center of the circular path or the center of the circle, you could also say center of the circle. And this is the force that's required to keep the object in circular motion. Now you could add the same thing in the acceleration definition also, that the acceleration is perpendicular to the velocity and is directed towards center of circle. You could add that also over here. Now, if force is equal to ma is going to become mv squared over r. Now, one thing that you need to remember for centripetal force, that this is not a new force. That is not a new force. This will just be some forces when added together. They will have a component towards the center of the circle always that will sustain the circular motion. Now that we have defined centripetal acceleration and centripetal force, we can easily define what is circular motion and what is uniform circular motion. So circular motion, you can see a motion of an object where its acceleration is perpendicular to the velocity of the object or to its velocity. Similarly, what about the uniform circular motion? So uniform circular motion will have just one thing. So it's the constant speed. So the motion of an object along a circular path at constant speed where the acceleration is perpendicular to its velocity. That's it. That's it. Now, something that could be asked about the uniform circular motion. So now a question that can be asked that if an object is moving at a constant speed, what quantities vary during that? So quantities that vary during uniform circular motion. Now, speed is the only thing that is constant, but the quantities that vary are velocity. We know the velocity is changing. If the velocity is changing, that means there is acceleration. However, acceleration itself is also not constant. Since acceleration is a vector, its direction is also changing. So the centripetal acceleration also is changing because the direction is changing. And if centripetal acceleration is changing, so is centripetal force. Again, the magnitude might not change, but the direction is changing, and that is enough for that quantity. Similarly, if the velocity is changing, the linear momentum is changing. And last but not the least, which is a forgettable quantity, angular displacement. So angular displacement is changing constantly over time, but that is still changing. So these are the quantities that are varying during the uniform circular motion. Now, this was the required information for you. However, there are certain examples that come again and again. There are certain patterns that are repeated for the numerical questions, for derivations, that we must go through them. And all of them rely on a simple fact that centripetal force is not a new force, it's just some forces that are added together in that particular direction. So let's look at the examples of circular motion or examples where circular motion is used. The easiest one is the vehicle turning on a straight, on a circular track, on a flat circular track. So what that means is you have a circle and you have another circle. So this is a flat, so that means this is unbanked. There's no banking involved. So your object is going in this direction. That means its velocity will be like this. Now, what does this mean for the rest of the quantities? What does it mean for the centripetal force and centripetal? Where is that centripetal force coming from? And how do we write that? So basically, the friction between the tires and the road, surface of the road, provide the necessary centripetal force. That means that the centripetal force that is coming is due to the friction force. Now, one important thing we know about the friction is that friction has a limiting value, has a limiting value, or it has a maximum value, you can say. So the friction between the tires and the road can only be so much. What does that mean for the centripetal force and the velocity? We know that F is equal to mv squared over r, where F again is provided by the friction. So friction, centripetal force. And the rest of the quantities mv and r we already know. So the way to look at it, if r is constant, if the radius is constant, if the driver is keeping a constant radius, and obviously m is also constant, then that would mean that f is directly proportional to the square of velocity, which would mean mean simply is that increasing velocity would increase friction. Okay. Similarly, if the speed is constant, if v is constant, then f is inversely proportional to r. What that means is increasing radius reduces the centripetal force, or reduces the frictional force, or the centripetal force. You can call it centripetal force, centripetal force. And since we said that it has a limiting max value, what if that max value has been reached? So if F friction that has become constant max value, then that would mean that if F is constant, M is constant, then that would mean V squared is directly proportional to the radius, which would mean that increasing velocity beyond the max limit, the max friction level, would cause skidding and it would increase the radius of the path. So what that means is if the frictional value is maximum and we still want to increase the velocity, what it will do is the vehicle will slightly skid towards the higher radius. This is what the math is telling us what would happen. Now, what if the track was banked? Then we have vehicle turning on a banked track. For that, we just need the components required. So this is the banked track, and let's say this is the car or the vehicle, whatever that is. We know the forces involved. We know that this is going to be the weight. This is going to be the normal reaction force or normal contact force. This time we don't need the uh, frictional component this time. So if we resolve either weight or the reaction force, so this would be our R. Should it be R sine theta or R cos theta? So for that, you need to just, remember a few basics. We know that this angle is theta, which we are very familiar with in the trigonometry or basic rules for parallel lines. Then this angle would also be theta. This means that this is the R cos theta, and this in this direction would be your R sine theta. This direction is where the center of the path is. So this means that since there is no motion perpendicular to the track, the R cos theta would be equal to mg, which is our weight. And similarly, the R sine theta would be equal to mv squared over r. So basically, the friction is provided by a component of the contact force. Okay, so we can write this first before we go into the derivation. So, sorry, not friction, centripetal force is provided by, so centripetal force is provided by component of normal contact force, a normal reaction force. Practically speaking, there is a component of friction involved also, but in A levels, for simplicity, we are not considering that. However, let's continue with the working. Now, R and R are the same, theta and theta are the same. So to solve these simultaneously, R sine theta over R cos theta would be mv squared over R divided by mg, which would be mv squared over R mg. Notice that m and m can be cancelled out, leaving us with v squared over rg. On the left hand side, r and r get cancelled, leaving us with sine theta over cos theta, meaning that this is tan theta over v squared over rg. Now, let's examine this the same way we established the relationship between them. So if theta represents the angle of the banking basically, so if theta is constant, then v squared is proportional to r. This would mean that increasing velocity would require increasing radius of curvature. Similarly, if r is the same, if radius is kept constant, then v squared is proportional to tan theta, which loosely means that increasing velocity would require increasing banking angle. Again, at this point, we are keeping the radius constant. And uh, that's about it. The third condition is kind of obvious already. If we keep v constant, the velocity is constant, then r would be inversely proportional to, or tan theta is inversely proportional to r, which again, uh, what does that mean? This would mean that to increase, uh, let's say to decrease radius at same speed, a higher banking angle would be required. So again, we are looking at this from a practical point of view, from a physics point of view. So this is what the math is telling us also. Now, let's look at another example which you can encounter in the past papers also, which is conical pendulum. Now, this is not the same pendulum motion that we are used to. It's the conical pendulum, which means that the motion of the pendulum, oh, sorry, is circular. Now, we know that there is going to be a tension force. The tension, we will represent it as F. This is the object. It will have weight mg. And let's say that this is the length of the string L. We have the angle of the string theta. So since there is an angle, we can resolve the tension into two components. So this would be F cos theta, and this would be F sine theta, and obviously this is the radius of circular path. Now, one thing to notice before we go anything, if you look at this, we have a sort of a right angle triangle situation. So, so this is L, this is theta, and this is the radius. So R can be written as L sine theta. This is an information that we will use later on. Now, a component of this tension force is providing the necessary centripetal force. So F cos theta is equal to our mg, and F sine theta is equal to mv squared over r. Normally we would, like, when we repeat the same thing, we will have a thing very identical to this equation. But since this is a pendulum, we are more interested about the time period also. So we are going to use m r omega squared. Since omega is 2 pi over t, the omega squared turns into mr 4 pi squared over t squared. Now, when we compare these two things the now when we sorry not compare when we solve these simultaneously, f sine theta over f cos theta equals to mr 4 pi squared over t squared divided by mg. We can cancel out the f and f, but we don't need to cancel out the sine theta, or we don't need to turn it into tan theta yet, because r is L sine theta. So this would be m times by L sine theta times by 4 pi squared over t squared divided by mg. We can cancel out the m and m, leaving us with, now we can cancel out the sine and the sine. So this would be, we can now cross multiply. So this would be 4 pi squared L over t squared g. Cross multiply, this would get us t squared equals to 4 pi squared L cos theta over g. Now, this would mean that when we do t, that when we take the square root on both sides, we get 2 pi square root of L cos theta over g. Now, the relationships that we can infer from this equation. So, if theta is kept constant, then t is directly proportional to the square root of L. Now, we don't need to talk about more than that, because we know that if we increase the length of the string, the time period would increase. This is as simple as it gets. But if L is constant, the length is constant, time period would be proportional to the square root of cos theta. Now, what does it mean by cos theta? We know how cos theta goes. Cos theta goes like this, where this is 90 degrees, this is 180, this is 270, and this is 360. And theta, remember what it was It's this particular angle. So this would mean that when cos theta is 90 degrees, obviously there will be no tension because cos theta would be 0. But when the angle is 0, you would have a maximum tension. That means straight down. In between these 2 points would be somewhere intermediate. So this was an easy derivation to understand. Now, there are 2 types of vertical motion that we need to study. So this was the third one, vertical circular motion. Let's say this time it is with a string. The object is held together by a string. So what that means is you have this centered over here, and you have string passing through the center. This is your object, this is your object, this is your object, and this is your object. Object has weight that goes downwards, that goes downwards, that goes downwards, that goes downwards. Tension always goes away from the object, away from the object, away from the object. Let's call these A, B, C, and D. Now, we need to examine this situation over here. We need to examine what are the equations of centripetal force at each of these situations. So at A, you have both T and mg towards the center. So that means T plus mg, both of them are contributing to centripetal force. At B and D, you have a similar situation where T is the only contributing factor to our centripetal force. C, on the other hand, it's T minus mg that is equal to mv squared over r. Now, a further examination which is required. If you make T the subject, this would mean that this is mv squared over r plus mg, and over here, sorry, minus minus. And in this case, it would be mv squared over r plus mg. Now, what do these 2 equations tell us? What does this minus and the plus indicate? This indicates that this is where T, tension, is lowest. And this is the point where tension is highest or maximum. Another observation that we must understand over here, that to maintain circular motion, T has to be greater than 0, right? If there is no tension, there is no circular motion, right? We already know that the object would fly off tangentially. So to maintain circular motion, T, even the lowest part, the lowest T has to be greater than 0. That means mv squared over r minus mg has to be greater than 0. So that would cancel out the m and m, because you can take m on both sides. This would mean that your v squared over r has to be greater than g. Now v squared over r is your centripetal acceleration. So your centripetal acceleration has to be greater than g. So let's write it that your centripetal acceleration has to be greater than acceleration due to free fall, or g. This is the condition to maintain circular motion. To retain, or sorry, if the object remains in circular motion, that means that this condition has to be met. Now, a similar case of vertical motion where it's sort of like an object moving in a circular path, sort of like a car, but instead of a tension, it's a normal contact force. So the picture will remain the same, but it's just a few minor changes that would change. So this was the fourth one, vertical, vertical motion, but sort of like with a car or a toy. So this is this. Let's say this is your object now. At the sides, we don't need to know anymore because we know that it's the normal contact force that it's going to be present. So this is the normal contact force. This is the normal contact force. So R, this would be R, this would be R. This would be mg, this would be mg, this would be mg, and in the same direction would be mg. So A, B, C, D. So B and D would be the same case as before. But at A, again you have contact force, reaction force plus mg equals to mv squared over r, which means that r is the mv squared over r minus mg, and this is the lowest value of reaction force. This particular value has to be greater than 0 at all times. And at C, you have R minus mg equals to mv squared over R, and that becomes R is equal to mv squared over R plus mg, and this is the maximum value of reaction force. So as we did before, the lowest R has to be greater than 0. Again, we would have the same thing. So acceleration has to be greater than g. Acceleration has to be greater than g, the centripetal acceleration. Now, this was the case if the object is maintaining its velocity. So this would be exactly the same if v is constant, if we are maintaining a constant speed. But what if we are not maintaining a constant speed? What if we are propelling it one time at the bottom and the consequent motion we can study? So same vertical motion, v is not constant. So for example, this you will find in past paper also, that you are providing an initial speed. You are providing an initial speed, some speed over here. Let's call it u over here. You're providing some u over here. So obviously, initial velocity is provided only. That means this car or this toy has to go through all the uh, locations of the loop. And again, this is vertical, so it will have some height change also. So what we have over here, it will be a similar problem over here. That the reaction force over here, this is going to be R and this is going to be mg, that R plus mg is equal to the mv squared over R, and to be able to do that, R has to be greater than 0. R has to be greater than 0. So this means that we will again end up with the same problem. V squared over R has to be greater than G. But the V over here is this. This is not the same U. So how do we get V over here? So V will come out with the change in gravitational potential energy and kinetic energy. So one thing we know, so the EP change is mgh, and the change in kinetic energy, we know that V is less, so V is less, so it's going to be half m u squared minus half m v squared. U was higher. M, M, M gets cancelled, leaving us 2 goes on the other side. So you get U squared is equal to 2GH plus V squared. Now, V squared in V squared would be U squared minus 2GH. So V squared over R. R is basically half of H, so divided by R, V squared over R would be U squared minus 2GH over half of R, sorry, half of H and half of H. So what does that get us? H and H gets cancelled, leaving us with 2 U squared over H minus 4G. And this is greater than G itself. So this becomes 2U squared over H minus 4G greater than G. So when you simplify this, this becomes 2U squared greater than 5G. H goes on this side. So U squared would be 5GH over 2. Therefore, U would be greater than square root of 5GH over 2. I hope I did not make any mistake over here, but otherwise this is what it would look like, that our initial velocity has to be greater than this square root value for the object to remain in contact with the loop. Now, these were just the examples of how you can use a little bit of math and forces, understanding of forces, to be able to calculate some necessary information. Hopefully in the next video, we will look at some past paper questions of this topic, and we will discuss them then. Meanwhile, if you feel that you like my method of teaching, if you like this video, so don't forget to subscribe to our channel, like this video, share with your friends, comment, and reach out if you feel that I wasn't able to explain a certain concept properly. And see you in the next video then. Bye bye.